So what comes now is basically just the long calculation on two examples, and I'll try to do them kind of in parallel. In both cases, we will be computing the Nambu-Goto action, right? The equations of motion coming from it, and actually we will not solve the equations of motion. We will observe that by energetic considerations, you can say a lot. And so the goal here is going to be to compute the separation between the quark and the anti-quark, and the energy between the quark and the anti-quark from the Nambu-Goto action, right? So that will be the goal. So let me first rephrase here the metric for ADS space.
How can you determine L? I thought that was part of the data.
Tell me again.
L, I thought was part of the data.
No. Okay, yes. It's going to be part of the data if you want, or if you want, as you will see, it's going to be a quantity that you will determine, right? You will see, depending on the how much the string enters or not this space, this L will take a different value, right? We will make a plot now, okay? But the idea will be that this L is a data in the sense that you can vary it, right? And then you see how the energy goes, right? So the idea will be to get an expression for the separation in terms of string quantities, to get an expression for the energy in terms of string quantities, and then to get an expression for E in terms of L. And that's the thing that you will be interested in. Okay? So let me rephrase and write. So following the comment by Jose, we will consider string that moves in ADS, but is not doing anything on the sphere, right? So we will ignore whatever happens here, and the result that will come out basically will be independent of a sphere being there or anything else being there. And so in that sense, it will apply to lots of four-dimensional conformal theories, as we will discuss tomorrow. The parallel example will be to do the same calculation, and it's very instructive to do it in parallel. For a metric where there is a time-time component, XX component, radial component, and then some internal space. And we will really not care about what this is, right? So the strings that we'll be studying in both cases, there is an answer that is like this one. There will be X equals sigma, T equals tau, and U a function of sigma, okay? Notice, by the way, as I was discussing on the break with some of you, there are lots of solutions we are not considering here, right? So, for example, U could be a function of sigma and tau, right? Things should not necessarily separate so nicely. Aside from the string not exploring the sphere, there is an answer that is very restrictive, right? For the present purposes, it's okay, but of course, people have made a point of studying more general things, and that's, people have made a lot with that, right? So people still work on those kind of things. Let me see. This. Okay, so given the same answers, let's compute the induced metric. So once again, this is the answer. The induced metric on the worship of this string is going to be the following. I hope this is clear to all of you what's going on there. In this case, it's going to be something like this. the only thing that I'm saying is that rho is a function of sigma and that u is a function of sigma explicitly. Now you can see it's very simple to see that as a matrix where you will be separating these four components. This is just a this is the matrix here. So the determinant of this that is the thing that I need in the Nambu-Goto action, by the way. And changing the sign, that is the thing that I will need there, is given by, in this case, this is in this case.
Excuse me, what do you mean by the U prime?
Okay, very good. So you see U is a function of sigma.
Okay, so
Du sigma is what I will call U prime, and the only is, look, it's a very silly thing. I'm just writing, instead of du square, I'm writing U prime d sigma, right? So that's why I'm putting here d sigma. Okay? Okay? You okay? Any other doubts about this? Because this is the most complicated part of the calculation, really. So all the rest goes almost flows by itself. Is this okay? Yeah. Great. That's the determinant of the induced metric there. The determinant of the induced metric here, as you can check with not much more difficulty, is given by this. And just let me follow the notation that you will find in a bunch of lots of papers. Well, you're calling this quantity f squared and this quantity g squared. So this is this, and what you will need actually is the square root of this. That is going to be this. And what you will need here is the square root of this. That's going to be this. Okay? Okay? So then you go one more step, and here there is something that I should correct. Actually, I want this one. Yeah, okay, this one. The Nambu-Goto action is roughly this one, but to be completely correct, this is the string tension, okay? 1 over 2 pi the string length squared. So I put this factor there with care, just to be careful in what I'm going to write now. That is the fact that the alpha prime will drop from this calculation. This is the action here and here. Okay, so these are the two actions we would like to work with, and if we're okay up to here, all the rest is just algebra. Is this okay to everyone? What was the assumption? What's the induced metric? What's the determinant? What's the action?
Alpha prime to the other side.
Say it again.
You get the alpha prime to the other side.
Which side do you want me to take it?
If you're there,
Yeah. So look, the action. Let's look at the number go to action. This line here, 1/2 pi alpha prime. That thing. Okay. So I make it particular for this metric, and due to this factor, the induced metric. Okay. Or if you want, the induced determinant has this. So you agree that the square root of the determinant is something like this. Yeah. So you agree that it will cancel with the 1/2 pi alpha prime. But it will not there because I'm not telling you what GTT is, etc. Right? Of course, in a particular example, it will happen that these things will contain alpha primes, right? But okay. Are we okay with this? Good. Good. All right. You see, this is an important point that I'm only making. It's beyond the just algebraic thing. That is, in this case, the thing will be alpha prime independent, etc., etc. And not necessarily in all the examples that will occur. Okay. We will comment more tomorrow about this point. the fact that the thing is erasing the alpha prime here is that behind you have a conformance theory, and in a generic example that will not necessarily happen. Okay, good. So I would like maybe just to keep this formula and this one and go with it. So maybe let me try to do it all in this black box and just make a line. Yeah. So basically let's look. So let's so this is a generic example for the ADS example, which has have that thing that I wrote there. So notice that in both examples, the fact that this thing does not depend on this tau here and there allows you to do that integral explicitly and basically call this capital time. It's the time that this string is propagating on. Don't confuse it with the tension of the string tension or something like this. Just the this is going to be kind of an static solution, and time is passing by. Okay. Very good. So now, yes, I need this. So you see, in both these examples, it's happening. Now you see them, and they are just examples in classical mechanics. Right? They are just examples in classical mechanics, where okay, the Lagrangian, the thing is ugly because we never in classical mechanics found Lagrangians where the kinetic term is inside the square root. Okay, in that sense it's ugly, but okay, it's just a classical mechanical system. And notice that in this classical mechanical system, the Lagrangian, the thing inside there, is not explicitly depending on sigma. Okay, sigma is now your time, to say it somewhat, right? So sigma is the thing you are deriving you are writing your kinetic energy in terms of. So nothing in there depends explicitly on sigma. So yes, okay. The fact that does not depend explicitly on sigma allows you to write a conserved Hamiltonian, right? As we know from classical mechanics. So this conserved Hamiltonian, in the ADS case, and in the generic case, well, the expression, you know, here is given by that. So when you do this calculation, and really it will not take you long to check this, it's just given by this. In that case, and in this case, this concept Hamiltonian is how we should think about this problem now. Now let me perhaps erase a bit here. So it's clear to all of you that this quantity is a constant, this quantity is a constant. Yes? So it's a constant quantity here. So let me try to redo this plot in a slightly different way. That's going to be the following. I'm going to plot here the x direction. I'm going to plot here this radial coordinate u. And what's going to be happening here is that this string that one is hanging and that is entering in some way into this space, okay, it will describe that contour we are discussing in this space and time, right? We are not plotting that bit. And it will enter in the space up to a distance, let's call it u0, okay? And the goal here will be to find this separation, or the first goal will be to find this separation and the energy between this quark and anti-quark pair. Here is the quark, here is the anti-quark, in terms of this length u0. Okay? So I hope the picture is more or less clear. If it's not, it's now the moment to cry about it, but I think it's more or less okay. Is this okay? Yes? Can you follow the thing? Good. So notice the following. This string is going to be moving here, and what will happen at this point is that u prime is 0. So which is very clear, right? The thing has a minimum there, has an extrema there. So if u prime is 0 at that point, you can characterize this constant by saying, okay, I will just pick this constant to be the value of this at u prime equals 0. Okay? I will just take the constant to be that. So I will call this this. Let me see if I make it right. Yeah.
Shouldn't be, I mean, previously we had u squared over the first, and then we had,
Tell me where I'm making. Tell me where.
I mean, we had the action, and previously when you were deriving it, you had u squared, and you switched it to u to the form.
No, but wait, let's see. The action, you agree on this and that?
No, not on the second one.
Oh, you don't agree on this? Okay, let me see. Let me
U
check.
squared over r to the formula, and then u to the form.
I think
No,
it's
it's correct.
I think it's u to the 4. We can check it in a moment. Look, let's go over the.
Computer determinant is correct.
Yes.
Okay.
Look, remind me how was the induced metric. So it was u squared over r squared,
Okay, and then
u squared over r squared, plus r squared over u squared, u prime squared, right? So the determinant, okay, this has a minus, etc. The determinant is u squared over r squared times u squared over r squared plus r squared over u squared, u prime squared. And I want to write it in a way such that the u prime gets alone, so I'll take this out, right? It will cancel with this, but here you have this. You okay?
Yeah.
All right, good. Any other doubts about this, or we are happy with this? So you see, this is just a choice, but this is a convenient choice. It gives you a better picture of the thing. To call this constant, that it is a constant, equal to the value of that thing when it turns around, and same here. If now what we are supposing is that it's exactly the same picture. Instead of calling the coordinate u, I'm calling it rho and rho c. I'm calling this radial coordinate rho and rho c. Okay? Okay. So you see from here, from this equality or from this equality, if you square it, etc., and do a minimum amount of algebra, you will get an expression for u prime or u prime square, and this expression will read in this form. Just let me cut to the chase. du sigma. So basically getting this from here is going to read like in this way. And in this case, it will read like this. Okay? Tell me if you agree, but it's more or less visual that the thing is something like this. Yes. By the way, there is a very simple way of checking this, that is the following. Notice that in the ADS case, let's look here. In the ADS case, these two functions, f squared, that here was gpt times gxx, and g squared, that here was gpt times g rho, radial coordinate. So in this case, in the cases of ADS, f squared is alpha prime square u to the 4 over r to the 4, and here it's just alpha prime square. Right? So one can check that the expressions go to each other. This expression that I have here goes into that one once you cancel the factors of alpha prime, etc. Okay. Okay, good. So you see from here, from here, I'm noticing that the separation between the quark and the anti-quark is just, notice we are calling x this direction, it's just x, so it's the integral of dx, or what's the same, the integral of the sigma, because x is sigma in this parameterization we have done. So you can, from here, write the separation between the quark and the anti-quark pair as an integral that instead of doing it in sigma, you will do it in u. Right? So that's the goal of the thing. Just write it in terms of an integral that knows about this extra fifth dimension. And it takes this expression. And in this case, it takes this expression. So how this is to be thought? What you are doing here is an integral between the lowest point reached by the string the integral is with lower n rho 0, and the highest point reached by the string. Okay, so here comes the following thing I should clarify. We will be putting this n at infinity. Okay, we will be putting this at infinite distance. Okay, and I will say what's the physics of that. The physics of that is the following. You could think, and I'm sorry if this comes in a contrived way, you could think that the mass of these two quarks, quark and anti-quark that you are putting here, is related to the mass of strings that extend from here to here. Okay? I was trying to make the point when I was discussing the Wilson loop in the Wilson way, right, in the first thing, that those quarks were not dynamical. They had not a kinetic term, or they had an infinite mass. Okay? So the way of implementing that infinite mass, non-dynamical behavior of these two external points is to place them at infinite distance. Okay? So they will have, if you want, infinite mass, and hence making them non-dynamical. So this is this infinite here. Is this clear physically what's going on? It is or it's not? Please, it's a moment to complain. Especially the young people.
Carlos, that would be F, rho naught, I guess. This D.
Here?
Yeah, I mean equation above under the
Yeah,
square root you should have F rho
minus-
naught.
Not G squared, but rather F
Yeah,
naught of
F
rho
rho
naught.
naught
Yeah,
square.
you're right. Right, and this is the thing that blah 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 comes here.
Yeah,
Yeah.
sure, yeah.
Okay. Good. Any other complaint up to this point?
Can you explain again where you're taking the infinity limit?
Very good, very good,
Like,
very good. So, Wilson, let's go back to Wilson. He tells you, look, introduce two external sources in the system. In other words, introduce two things with no kinetic term, no cinematics, no dynamics. Okay, very good. So, Joan was asking me during the break, how do you think this thing, right? How do you think, why is a string, etc., etc.? Why the proposal is with a string? So the way you think it, let me now try to physically motivate a bit more the thing. The way you think it is the following, or the way perhaps this was thought originally to propose the analogy between the Wilson loop and the string moving in the space. This perhaps should be thought in this way. Okay, so you will have some, let me be this the radial coordinate of whatever space you have. So you have a bulk, you have, if you want, some boundary, okay? Very good. Now, this is type 2B string theory. There are no open strings in this theory, okay? But as you know, you want to put an open string, you have to put a D-brane, okay? Good. So what you're doing is you're putting a D3 brane at some position, and okay, these strings, by the way, they will have to close somewhere. These strings, they will represent, because they are fundamental strings, they will represent, in the field theory, they will represent fundamental particles transforming the fundamental of the gauge group. Okay, so these are your quark and anti-quark, given an orientation of the string. Okay? Right? Okay, how can you make this quark and anti-quark be non-dynamical? Okay, give them a very large mass. Okay? In other words, separate this string, this D-brane, from the branes that originally were the branes where the field theory lives. Okay, this is a very picture, right? So these words should be taken with more than one grain of salt. Separate the branes of the gauge theory from the branes where you're going to put your string to end by a very large distance, and that distance will be related to this mass. Okay.
Okay.
Okay. So that's why I'm going to do these integrals up to infinity, or I'm going to give these external quarks infinite mass. Okay? And the integral is from the minimal distance, because then what will happen is that, okay, this will not be the situation. Once I replace all this by ADS space, okay, the strings will accommodate in some way, etc., etc. Okay? And again, these are very words, right? So this should be taken really with a grain of salt. So as words, I don't like to say them, and perhaps in not saying them, the thing becomes less clear, but I think they are somewhat misleading saying this, but okay, it might illuminate some other aspects.
Carlos, just for the sake of the discussion, if you wouldn't have used this argument, the one that you have just given now, in the mathematical problem that you are solving, you have until the sitter.
Yes.
And
at least on this side.
The physical length L, if you compute it in terms of the coordinate U, has to go to infinity because that's where your boundary is.
The physical length L, oh, look at this. So let me now go back to this picture.
Right. That line that you
This
wrote
one.
there is at U infinity actually.
Which line, sorry? This one.
Yeah.
Yeah, this one, I'm putting it very far away, yes.
So
But notice that this distance will depend on how much this string enters up to some you see.
no, I don't
That
disagree
will-
with that. I'm just making a comment about the upper bound of that integral.
Yes, but if you want, what I think that Jose or many other people were wondering is why you put this at infinite distance. right? In
Oh, wow,
principle,
okay.
you could place this. This is something that you know, but let me say it for the young people. You could place a D3 brain on ADS5 crosses 5 at any point you wish, right? It's a BPS object, so it will not decide to go very far or come very near. At any point is good. It's a BPS object. So you could place it here or there or there. It's a physical requirement if you want to place it very far away to give these quarks a very high mass in the sense of these plot and words I was saying. I hope this is more or less clear. So let's go a bit more with this calculation, because it's quite nice the fact that that integral can be done explicitly.
So sorry, just to go back to this point, I mean, the commenter John, you're assuming this interpretation that the space, the 3 plus 1 dimensional space-time is the conformal infinity of ADS5.
Yeah, I think that intuitively I thought that was
Okay.
the right thing to do.
But
Intuitively,
I thought we're not necessarily as, or you made the point that you didn't want to think of it like that.
look, I don't want to think it, okay, very good. It's not wrong to think it that way. I prefer not always to think it that way. Can I comment about this in a while? Because it's a long tour for, let's go a bit more with this, and let's write it here. So, Joan and Jose comment, and we will discuss it, so that you will not make, I will not forget. So it's quite nice the fact that this integral can be explicitly done, and it will not surprise you that it involves some kind of special function, but when you evaluate it between two limits, you will get an expression for the separation between the quark and the quark in terms of how long, how much the string or how long the string is going into the bulk. Okay, that expression in this case is given by this. So this, the fact that the separation in terms of U0 is a monotonic function like this, okay, is telling you quite a bit, right? It's telling you that the more this enters into the bulk, the more separated is there, right? And that in principle, when U0 goes really very small, that is, the string comes really, really very close to here, the separation goes to infinity, okay? All right? Very good. On this side, you cannot do that because you don't know what the functions f and g are, right? So that will depend on the background. This I was saying is for a generic background. Okay, so let's keep it there, but generically it's just this. Now, the point is to compute the energy. In these examples, or if you want, it is more or less intuitive that the energy between the quark and the anti-quark pair will be related to the Nambu-Goto action in the following way. Okay? Because at that level the problem became an Euclidean problem, so the energy, the action is always the energy times time, right? At the level of probably there, right? Start blackboard up or those two entries there. So if you want and you take that expression for the Nambu-Goto action, you can in principle compute the energy. So notice what happens. Let me do this with some detail. If you compute this, again this is on the ADS5 case. If you compute this, you will get and this is probably what I have there in the box. And if you now use the fact that this sigma is given, this sigma in terms of the U is given by this second expression here, you can write this, the energy for the quark anti-quark pair, in this way. Okay, just let me write it briefly because So all I'm using here is this expression where I'm replacing this sigma by this sigma there, and u prime squared by that thing there. Okay, so there are two replacements here, but the algebra, believe me, is kind of straightforward. So if you look at this integral, you will see that for large values of u, the integral goes like du, u squared over u squared, so it goes like the integral of du, so it diverges. Okay, right? So naively, this is telling you that the energy for the quark and anti-quark pair is infinite, right? So you should somewhat regularize it, because what's going on here is that you are counting, when counting this energy, you are counting the infinite mass of these quarks. That's the infinite that is hitting you there, right? That's this, if you want, a linear infinite that will appear from here. That's the mass of these quarks. So you should discount, renormalize this, regularize this if you want, by discounting the mass of the quarks. There are different ways of doing this regularization or normalization. There is a very nice way in a paper by Gross, Oguri, and Drucker. Let me just tell you the bottom line of the thing, or the simplest way of thinking, the way of regularizing. Well, it's just subtracting the mass of two rods, the mass of the two quarks that just hang from here like this, right? So that's the way of taking out this infinite. This infinite, we are saying, is the mass of these quarks. Okay, good, let's take it out. So to that expression, I will subtract the mass of two rods, if you want, that go from here to the end of the space, from infinity to the end of the space, and whose action is just the action for a string that is like this. All right, so that will be the way of regularizing here.
Why are you going to the end of the space instead of just to use
I should go up to here.
Yes,
I should go up to here. Yes. Yes. You will see how this bit will count in a second. But there is just an algebra, so I should go up to here. Up to where the string gets, right? The thing is that, as you can see from this expression, the more I stretch this, the more will go into the end of the space. So after all, what always happens is that all these integrals are done from 0 or the end of the space up to infinity, right? So, but you are correct. I should take out an infinite, that is the infinite mass that I'm getting from here. As it's clear to you, look, there are different ways of renormalizing, right? So why don't you just take up to here? Because in any case, you are taking an infinite, right? So these different ways of renormalizing, actually, that's why I'm mentioning this paper of Gross, of Oguri, that gives exactly this result that I'm commenting about. It's like taking the infinite mass in the way I'm saying, but in principle, these are just different schemes of renormalizing, right? So, or this is kind of a preferred or nicer one, but just that. So the thing is that what I would like to do is translating this into this. Let me now come back to this expression. What one would like to do is to okay. This same expression I have here and to this I want to subtract the action of these two strings. Notice that okay, this you can do it in some detail, but the Nambu-Goto action for strings that are just like this is given by the square root of GTT times G rho rho, right? Because these are just rods that extend in the radial direction. If you look at the parameterization of the string, these are rods that extend in the radial direction, and okay, as time passes. So this is the Nambu-Goto action for that string, right? It doesn't have, if you want, a kinetic term, a u prime square term. In this perspective of ADS, is just subtracting a 1 that is precisely the one we are getting here. But in general, is given by that. So in doing this subtraction, by the way, I should subtract not one, but two of these. Two of the actions of this thing. And you can do it either here or there. This subtraction should be done also in the generic case. You will get an expression for the energy that looks like this. So let me write it in the generic case. Let me write it in the generic case, and then we'll evaluate it for ADS. It will read like this. So this is the term that you are subtracting. You see that GTT times 0 rho is what we are calling G, somewhere there. And this is the term that you are subtracting. So just let me give you, and the algebra that comes from here to the next line is non-trivial in the sense that you have to do it. It's not something that you just look and you get. Let me just give you let me first rewrite the separation expression we had here. And let me rephrase, and this is something that it becomes useful in what will come. Let me rephrase the energy of the quark-antiquark pair in terms of the separation of the quark-antiquark pair, and it reads like this. So this is just, again, this is just algebra that I didn't check for today, but I checked many times in the past, and it's correct. See, my confusion regarding your comment was coming because of this. Here you are just rewriting, this is just a rewriting of that. You're just rewriting the thing from 0 to rho 0, right? You're just accommodating this thing, all right? So let's keep these two expressions, and just let me tell you what's the result when you do this regularization in ADS. You will get that the energy between the quark and the quark pair, again in ADS 5, the result is the following. So remember that the radius of the space to the fourth was related to this Toft coupling, right? So up to this factor of pi's and the gamma function, this is going like the square root of the Toft coupling divided by the separation. Okay, good. So there are many different physics comments that are worthwhile doing here, doing at this point. So let's go over that. Before this, is there any question about this, or let me say it in this way? Are these expressions more or less followable up to here and up to there? Then this is just involves some algebra, but is this more or less, can you follow what went on here, please?
How do you write that thing you have to subtract
So you see in the ADS case, let me do it here. So I had this expression for the energy, right, that involved one integral that we said, if you look at it at infinity, it's the integral of du. Okay? So you see what I'm saying is, look, what you will have to take out is the integral of the function g. Right? If you look perhaps above there, the function g in ADS is just a constant, right? So this is the one I'm taking out. And this is the one that I'm taking out that with this will give the finite result. Okay? Can you see? Can you see? Can you see that it can work? I'm not saying that you see it transparent here, but that it has the chance to work. Yes? Okay. Any other questions? Very good.
So in the expression for L, you still have a U0, right?
Yes. In the expression for E, you still have a U0. I'm just translating it here.
Yeah.
And all these factors, all this horrible thing, is the translation.
So you can say that basically E depends on that.
On U0, exactly. And you see, it depends linearly, right? So while the more it comes here, right? The more it comes here towards U0, 0, the separation grows, right? The energy decreases, okay? Very good. Here comes a set of interesting physics points. First point. This is given a Coulomb law, right? The energy or the potential between the quark and anti-quark pair is proportional to 1 of the distance of the quark anti-quark pair, okay? So this is a Coulomb law. Is it too strange that it's given a Coulomb law? No. It's the only thing that could have given. Why? Because this is a conformal theory, right? You are going to write a potential. A potential is something with units of energy, right? The conformal theory has no scale in itself, but you are putting this quark and anti-quark at a distance. You are introducing scale. So it's better this energy depend directly on that distance, okay? By units, if it's an energy, it has to be the inverse of the distance, okay? Good? So it's okay, the result, okay? It couldn't have given differently from a Coulomb law, given that this is a conformal theory. Good? What's very interesting is that if you do this calculation of the Wilson loop, we take this calculation and you do it perturbatively, right? You do it in perturbation theory, it will give you of course, it will give you 1 over L, of course, because that's the symmetries of the theory, but it will give you something like this. So you see that in going from weak coupling perturbatively to strong coupling, you deform a lot this function here, right? So in principle, the law is going to be for any coupling okay, something like that, right? This feature of moving from perturbative behavior like linear in lambda to non-perturbative behavior in square root is very typical of ADS examples. Good, but that's a interesting and important physics comment. What else I want to say? Notice that if we now plot the energy in terms of the separation, but it will give you something like this. Right?
Carlos, I just missed your last point. You said that it would be related to, I mean, sums. It would have some dependence on lambda.
Generically,
Yeah, right.
take this perturbatively, right? Compute that object perturbatively.
Right.
It will give you lambda divided by L. It
Yeah, okay.
cannot be otherwise. Compute it non-perturbatively. Very strong value of lambda when you use all this approximation, etc., etc., gives you this.
Right.
Generically, it will be something like this. Okay?
Mhm.
Finding this function, non-trivial.
Yeah.
Okay? But with all this integrability story, people are finding whatever is this function in a different observer. Okay? Which is a remarkable achievement, right? Because you are finding something for any coupling is remarkable. Very good. Those were physics comments about this ADS example. Notice the following. No matter what separation, what I want to say is there is not a maximal separation. You can separate these two quarks as much as you wish. Okay? So notice that there is a qualitatively there is strong difference with this example. Right? Not only because of the, okay, here is Coulombic and then is linear, so that doesn't happen in that case, but there is a maximal separation, right? So there is nothing like screening in n equals 4 super-Young means, okay? There is nothing like pair creation and mesons that go about their business without talking to each other. So here the quark and the anti-quark, they will always talk to each other, of course with a decreasing energy, of course. That's it's just like electromagnetism, classical electromagnetism. Okay. Let me see if I want to comment something else here. Yes. So the last comment I want to make regarding this is the following. And now let's come to this more generic expression. Here, this expression was derived in some background, right, for which we are not specifying what GTT, GXX, and GRORO are. So, okay, in principle, we just went over the same calculation and got these two expressions. Tomorrow, we are going to start specifying this for particular cases, and notice the following interesting thing. If it happens that you have a background such that this quantity is not a zero, when evaluated at rho zero or at the end of the space, then you will read a law where the energy is linear with the separation. Okay, you will be reading a law that is more like in this example, right? A law like that. Okay. Of course, there will be corrections to that law coming from here. It will typically happen in those examples that these are sub-leading in L for large L. Okay? All right. So I was commenting this because it will be a typical feature of confining backgrounds, confining in this sense, that for large separations you will have an energy proportional to L log. And this thing here is what people call the QCD string tension or whatever. Okay. So I wanted to close the Wilson loops here, and let me take 5 more minutes of your attention until 4:30 sharp to comment on something that will give us the entrance to the tomorrow's lecture. Before that, any comments or questions? Is this clear or super trivial or super boring or linear combination of both? No, more or less. Was it clear, the idea of the thing? Yeah. Okay. Good. So let me just comment on something that will give us the entrance for tomorrow's conceptually the entrance for what I plan to discuss tomorrow and in the following.
Sorry, I have a question.
Please, please.
Probably very stupid, but
No.
I don't really see where you're going with all of this.
Excellent. Look, look, it's a very fair question because this is a risk you run when you explain a calculation, right? So the only goal here was to get an expression for this interesting observable that I just erased, the Wilson loop, computed in n equals 4 super-Young mills at strong coupling, assuming that this conjecture is correct. Okay? So in all these lectures, we will assume that this Maldacena conjecture is correct, which is not a bad assumption, believe me, it's not a bad assumption at all. And in this case, what you are just seeing here is how this particular observable of strong interest for a quantum field theorist behaves, in this case, in terms of the separation. Okay? So you may say, look, what did you learn? That the law that was linear in the coupling turns into square root of the coupling, big deal. Well, it's actually interesting deal, okay? Actually, a more interesting deal is to get this.
But I could argue with you that you picked an observable.
Excellent. Very good argument. And I will tell you, in this case, this observable is somewhat particular. I agree. and that's why this happens. This happens. So what's going on here is that, again, for n equals 4, it's theory with so many symmetries, right? Many things will be untouched by going from weak to strong coupling, okay? But one thing that people did not know before is that this law, okay, is untouched, that people knew, but didn't know this, or it didn't know this, if you want. Okay? So let's consider this as an important thing, right? The moment lattice people can do lattice for n equals 4 super Young mills, they will be able to check if this is correct or not. Okay, so that this is an experiment that will check. On the other hand, on the other side of the blackboard, what I'm trying to aim is, look, assume that there are other backgrounds, not ADS5 cross S5. Okay? Other backgrounds, and we don't know which are them, and tomorrow I will start comment on that. These other backgrounds, believe me now, they will be dual, not to n equals 4 super Young mills, but other, perhaps more interesting, perhaps more dynamical field theories. Okay? More contentful than n equals 4. So this observable will so look, okay, you will compute it in the same way, it's the same story, and you will have to deal with these integrals, whatever they are. Okay? But interestingly, you can see that if this quantity turns out to be non-zero, you will be having a model for what would be a confining theory. Okay? This is basically the goal of this. Am I addressing your point?
Yeah.
Yeah? Okay. Good. Any other questions, John?
So, Ricardo, I guess that you will explain, it's precisely what you have just said. Tomorrow you will explain this better, but I mean, if I just take all the comments that you have given us, the dependence between the distance between the two non-dynamical quarks,
Yes.
and the arbitrary function f of rho naught,
Yes.
it's actually complicated.
Yes.
So your argument that this is going to be linear, I mean,
No,
it requires a little bit more of care. I
Of
guess.
course, of course. You see
It's
here.
not just that this is not zero. I mean,
Very, very.
because for instance, in the case of ADS, f goes like u naught square, and it just happens that u naught square goes like 1 over L square, so you get a 1 over L. So
If-
it doesn't vanish in that case.
Good. Let me say it in this way. In
How
when
do
you
say
make
that
this
your
operative,
condition is necessary?
very. I didn't want to go over this, but let me say. When you evaluate these things in a space like ADS, for example, that rho naught, or that end of that last point where the string can go, is the end of the space that is u equals 0, right? So you see that f should vanish at u equals 0. So it's like this term will be dropping away.
Yeah.
Okay? But as you are saying, there is one point that you're picking that is correct. Look, the dependence of the energy in terms of L, okay, here looks simple, but then here all the dots are hidden, right? Because how is L written here? I don't know. I mean, one should do it. And of course, if what you do actually is you compute E in terms of rho 0, L in terms of rho 0, and then you try to parametrically invert one in terms of the other. But again, and what you can see when you study this in detail for particular backgrounds, particular cases, is that here the law is not only linear in the happy cases in which this is not 0, but there are corrections that come from here, typically suppressed at large L. Right? And there is a lot of interest, or people have had lots of interest on these corrections, right? And have classified them, etc., etc. So it's a non-trivial problem, the one you are hinting at, and people have gone over it. Am I answering your point? Or, yeah? Notice that in the ADS case, this is a 0, right? When you evaluate it at the end of the space, right? So that's why this drops, and that's why you get this law, right? That is coming from the suppression in that case, right?
How important it is to make sure that the backgrounds solve your supergravity equations of motion for for
Very
this
good.
calculation?
Very good. So let me
Because
rephrase
we
your.
have assumed that this
Very
solves
good,
those
very good.
equations.
Very good. So let me comment on this. Let me comment on this.
We can discuss it tomorrow.
No, no, no,
Sorry,
no, but
I didn't
let-
want
let-
to.
Let me comment it now. Let me comment it now. I had to comment about other things, right? That I forgot what was the point, but it's already.
You were going to introduce tomorrow's topic conceptually.
Yeah. But this gives me a way of doing it. So, alright, let me introduce tomorrow's topic conceptually, and then I'll answer Joanne's question, and then I'll try to answer the question that you both had that I forgot which was. Okay? So hopefully you will remember which was. Okay. The first lecture we decided that it was phenomenologically a very interesting theory, and we said we are going to depart a bit from this theory, blah blah blah, go to strong coupling systems in general, etc. But never mind, let's try to see what can this conjecture teach us about a phenomenologically interesting theory. For that, we'll pick this one. Okay? Very good. So, field content wise, this theory has, okay, if you want gauge group wise, this is SU and C for any and C, and allow me to take QCD with SU and C, assuming that going from NC bigger than 3 will actually not change a lot the physics. Will change the numbers, but will not change a lot the physics. So gauge group wise, we're okay. Field content wise, we are very bad, because we have the gauge field in the adjoint, but then we have the quarks in the fundamental, and then the quarks in the anti-fundamental. Okay, so field content wise, n equals 4 and QCD really do not look alike. Symmetries wise, well, this one we said, look, preserves lots of SUSY, preserves 0 SUSY. Not a SUSY theory. It's a conformal theory. It's a Lorentz invariant theory. It's not a conformal theory. It has a global symmetry that we call R symmetry. This has a global symmetry that we call chiral symmetry, and a baryonic symmetry. So symmetries wise, they look very much not alike. Phenomenologically wise, or some first degree phenomenology, well, the Wilson loop gives you an energy that is 1 over L, right? The Wilson loop here, or if you want, just let me plot this. As we were discussing before, first you have a Coulomb-like law, then you have a kind of a confining regime where the thing goes linear, and then suddenly there is pair creation, and that. Right? So phenomenology-wise, at least at this level of phenomenology, not look at all similar. So your point may be, look, this is all very nice, but will teach me nothing about a theory like QCD or theories of interest, right? And I should say, look, first approximation, you are right. This comment, I'm making this comment because of the following. When your quantum chromodynamics or your n equals 4 super Young Mills are put at finite temperature or finite chemical potential. So in the presence, if you want, of a chemical potential, in the presence of a background of charges, it happens, this is experimental observation if you want, that computing with your super Young Mills at finite temperature, which just boils to the fact of adding a black hole to the metric we were discussing, or computing with your super Young Mills at finite density, which just boils to adding just some rotation into the metrics we were discussing, very well mimics the results between, the phenomenological results between this and that. So it seems like all these symmetries and this field content so different do not drive the dynamics when the theory is at finite temperature. Okay, so that's just an experimental observation, if you want, right? So people do experiments with QCD, right, at finite temperature or at finite density. They get their results. These plots can be very well mimicked by doing strong coupling calculations with n equals 4 supergeometric mills. In other words, doing simple calculations in ADS5 with a black hole, with a rotation, etc., etc. So I will not talk about this, though it's a really very important line of research. All this story you heard about the rig physics and all this kind of mixing between people in ADS-CFT doing physics of this rig experiment, things related to that, people of ADS-CFT talking to QCD people about finite chemical potentials and all that. All that is a very fertile ground, and it's basically based on the fact or on the observation that when you compute with n equals 4 a strong coupling and any of these two, then the dynamics very much mimics the dynamics of QCD at finite temperature or finite density, right? But notice the following: the moment you erase this and that, all these symmetries seem to be taking the dynamics into their hands, right? So notice, the moment you put finite temperature, there is no more SUSY, there is no more conformality, there is still this, right? This will change. So many things immediately change, right? But okay, this is something that is important to be said, that what in principle looks as a hopeless problem is not that hopeless. And what the topics of tomorrow and after tomorrow lectures are just how to go from here into some other system for which you can still propose a duality like the one we have been proposing, such that those systems will look more like QCD in any of these aspects, either having no SUSYs, or having a chiral symmetry, or having a phenomenology more like this, or having a field content more like this, etc., etc. Okay, so that will be the topic of the next two or three lectures. Very good. So, having said this, let me try to address Joan's point. And he's saying the following: look, in there, over there, in the first blackboard, I was saying, look, I'll have a gravity background and I will compute the Wilson loop and I will get these results and up to here. Right? So the point that you're making is that I didn't seem to worry to check that gravity background, GTT, GXX, 0 rho, whatever they are, do solve the equations of motion. Okay? So people have played, and I don't include myself in that because I really fear that game. People have played the following game. Let's cook up a GTT, GXX, and 0 rho such that Wilson loop like, or many observables wise, I'm matching the results of this. Okay? I very much dislike that game. I don't want to be critic of people who are not here, but I think it's a cook-up, right? And maybe it's just that I'm old, and I'm more of the times where backgrounds were obtained, and then physics was gotten from those backgrounds. So the way typically this went is that people were solving Einstein's equations, getting backgrounds, and then learning physics from those backgrounds. The proposal lately from many of these people is to not get the backgrounds, input the physics into the background, okay? And then try to see if the background teaches you something that you didn't input into it, okay? I didn't play that game at any stage, but I don't want to be completely dismissive of that. It's just a line of research that happens to be kind of popular at the moment.
You could ask, of course, what equations of motion do these cooked up backgrounds
Of
satisfy?
course,
Maybe
of
you
course.
can do something interesting.
Which is very difficult. Which is very so. For example, there is one of the representatives of that line are, and these are nice works. I just don't agree philosophically with them. Right? there is a list of papers by Elias Kiritsis, Umut Bussoy, Francesco Nitti, and Liuba Massanti. So the papers are correct. I just want to emphasize that. It's not that they compute wrong, right? They compute right. It's just that the way they think the problem is they will input the physics into the gravity background, okay? And the way they encode it is typically in a 5D gravity theory. So they will forget about all these complications of type 2B, etc., etc. They will encode it in a 5D gravity theory that will have this typical action, Ricci scalar, some scalar, perhaps some gauge field, though it's not needed, and some potential for the scale. And in order to have the backgrounds that they need for some of these results to be reproduced, they have to hook up, they boil everything to hooking up this potential, okay? Which turns out to be typically horrible, right? A function, a very contrived function. Okay, then you can say whatever you want, but it's non-trivial in the sense that, in my view, they are getting a bit more than what they put in. Okay, and we can discuss if this bit more is a bit more of it, or if it was put in any case, but that's another discussion. Am I answering your point?
Yeah.
You had another question, but
now I'm trying to be nice to these people. So from the perspective
Can
of
turn
string
off the
theory,
camera.
that's actually a very difficult problem.
Yeah.
Because there are many more degrees of freedom than the ones that they are talking about. I mean, this sounds like inflation. I mean, let's map our ignorance into an unknown potential, and let's fill the potential to achieve what we want. But the string does not see, at least at lowest order, does not see many of the fields that you do have in supergravity. And these are completely free variables. They are mute in this discussion, but the instance equations will feed back functions that
and
there
that's
could even be a solution, actually.
Exactly.
But
Let me say another thing of a line that philosophically goes very much in this line, but I think it has more chances of being successful. And it's all this line that Sean Hartnell, Gary Horowitz, etc., Chris Herzog, etc., have been pushing, that is using this for condensed matter, right? So as we were discussing yesterday, any ADS is dual to any ADS P plus 1 is dual to a P-dimensional conformal theory. So as we know, there are many condensed matter systems that they seem to behave like 2 plus 1 dimensional and conformal, most notably superconducting like systems. So people just say, okay, look, let's study them with an ADS4. Let's put a black hole on that ADS4, and let's see what can we learn about this. Okay. So that's basically the bottom line. Of course, it's more refined, and people have learned a lot, and there are lots of papers lately. Again, this is another line I didn't went in, but not because of being philosophically against. What I like about this line is that given that there are so many condensed matter systems, it's not unlikely that you will hit some of them at least by cooking up, right? While you see QCD, there is only one. So in your lab, you cannot fine-tune QCD. There is one QCD, right, with the mass of the U, mass of the D. You don't decide what are those masses. You don't decide couplings, etc. So it's more contrived. And this, again, is not saying anything wrong about the papers or the authors. It's more contrived to match that system in this way than match many systems in this way. Okay? Again, it's not string theory, it's not a rigorous thing, whatever, but it's physics. So one should not disregard that line. Okay?
One extremely naive thing to ask: if you have something, which is, random potential V of phi, which does not solve the background, then how do you use the? How do you use ADS-CFT here at all?
Let me say, they are solving equations, right? They are solving equations.
Yes.
But what they are cooking up is the potential, right?
Yes.
So, and they are cooking up the potential such that it fits the results from lattice.
Yes.
Or QCD.
Uh-huh.
Okay. what's contrived here is the potential.
Yes.
If you look at the potentials, and your first reaction is, this cannot be a description of physics, but okay, that's just a comment, right? So,
No, I guess
you
the
see what I
question is
mean?
why do you have any right to expect that this should work if you didn't start from, this is not something that embeds in
Good.
in
So
Yeah.
like
they
string.
will tell you you have no right to expect that this to work, but they will show you a set of plots where it works quite well, quite well.
But there
No, no,
might
what works
be
is a
15
recipe,
more
right? I mean-
plots which don't work, right? I mean, how do we know that those 3 or 5 plots are the things that work? There might be 15 or 1500 more which don't work.
In that sense, you have to believe in their honesty that they are
Okay.
studying to the best of their honesty, right? They are being honest. They are not hiding things from you, right? But look, you can think it in this way. So this line is just a refinement, if you want, of what was called originally ADS-QCD, right?
Okay.
So people in ADS-QCD, the string theorists were criticizing a lot ADS-QCD because it's not string theory, etc., etc. Maybe what one we are learning from all that is that lots of the dynamics of QCD was just ruled by symmetries of the thing that they are captured by this or whatever the solution is, etc. Right? So that's so I discussed that a lot with all QCD people, and their point. So their nice point was that, well, you are learning something, symmetries that you didn't know were ruling the dynamics or the masses or this or that particle. They seem to be doing so. So again, I think this line is easy to criticize, but it's difficult to disregard the amount of results they have. I don't, so in spite of me not working on that, right? So I'm not particularly critic or bitter towards that line. I would like to be very emphatic on that.
So what is the answer to Joan's question?
That is, which one? Sorry?
Well, how relevant is the fact that there's an underlying string back or not?
Oh, okay. Look, for me, totally relevant. Totally relevant. Yes, for me, in my view, it is relevant. I don't do things where there is not a string background, blah, 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 blah. Even more, I'm very wary of doing things where the string background has a singularity, right? I always tremble whenever there is a singularity, and my co-author says singularity, go, right? So, but I think, oh, but then the superiorit approximation is not good, and oh, I enter into all this psychological nightmare. Here there are singularities all over the place, and okay, people pull back, pull forward, and they get results. So, in my view, you should not do things where you are not solving the Eisen's equation, blah, 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 etc. But again, that's probably an old-fashioned way of proceeding, right? So, one should not disregard this. Right? And again, this is not at the level of physics, just the level of opinion.
Yeah.
So, I'm not the one who will tell you this line is all crap. It's not to me.
So I have a somewhat philosophical question. You said you put QCD and n equals 4 Gram mills in finite temperature, finite potential potential, they start behaving alike. Is this something particular to these two theories, or do you think that this is some sort of universal behavior of gauge theories, that if you put them at finite temperature?
Yeah. I think it's because you see, there is a very simple way to see that this is kind of universal. That is the following: in many of the observables that people compare between QCD and n equals 4 and at finite temperature and at finite chemical potential, especially at finite temperature, the sphere, the phi sphere, is playing no role whatsoever, right? Just like in this Wilson loop calculation we were doing for this particular one. So you could think about finding backgrounds that are of the form ADS5 cross whatever else, right? And they will describe conformal field theories where the number of supersymmetries will depend on what is the whatever else, right? And they are solutions of the string theory. And in all those cases, whatever was the calculation you are doing in n equals 4, since it was disregarding the phi sphere, will give the same result, because whatever is the whatever else, the calculation will be the same in ADS. Right? And those are typically results that match very nicely with results of this at finite temperature. So it all seems to be depending on the fact of having a horizon, and that's it. Right? In those, I'm thinking 3 examples, but in those examples. Right? Okay. Well, since you're all very tired, we will not answer, because, especially because I don't remember which was the question that.
It was the infinity limit, but I think
Which was the limit?
the
wrote
limit
infinity
of y
limit.
to infinity, but I think you could, at least to my satisfaction, you
Yeah.
answered.
If everybody is satisfied, see you tomorrow.
Thank Carlos for another